Today we will be measuring magnetic susceptibility of a solution using Quincke's method. Okay. So here, as you can see in this YouTube, we have filled a solution of manganese sulfate. Okay. It's slightly pinkish in color, but you will probably not be able to tell. So the idea is that this solution is a paramagnetic solution. So that means, like in the other experiments we have studied, magnetic dipoles that can be there because of electronic motion, electron spin. So every atom will have a contribution for multiple electrons. So every atom you can assume has a net magnetic dipole. So in the solution also, these manganese atoms will have their own dipole moments. So when you place this inside a magnetic field, what will happen? Individual dipoles will try to align themselves. Okay. There will be a statistical probability of how many of them will be able to align, how many will not be able to align. That will depend on temperature and a fundamental material property of this material, which is called susceptibility. Okay. So let's assume certain number of dipoles have aligned themselves around the magnetic field. So that means now if you take any volume inside this solution, that volume will give you a net dipole moment. Okay. Previously, without any magnetic field, all these dipoles were aligned randomly, so that the net dipole moment in any volume would have been 0. But now, because you have a magnetic field, so there is a net alignment along the direction of the magnetic field, and that is called magnetization. Okay. So dipole moment per unit volume is magnetization, and that dipole moment produced will depend on the susceptibility of your material. So this experiment is designed so that we can measure susceptibility of paramagnetic substance in a solution state. Okay. Alright, so what we will do next, so we have filled a certain concentration of that solution in this YouTube, as you can see. This one has 60% solution. So basically you will start with this and then you will dilute this solution and you will go to 40% and 20% and you will measure the susceptibility for all these different concentrations. How will we be measuring the susceptibility? So we have this tube with the solution, so we will take this one and put it in between the two pole pieces of this electromagnet. Okay. Now you see we have this electromagnet and we have this traveling microscope focused between in the region between the pole pieces. Okay. So what can you do with this traveling microscope? So basically this microscope you can make it move up and down, and there is a vernier scale attached to it. So you can take the readings from the vernier scale and the main scale that is attached to the microscope. So the first you have to determine what is the least count of this vernier scale. Okay. Now once we have placed this U2 in between these two pole pieces of the electromagnet, we will be applying a current to this electromagnet, which is controlled by this current supply for electromagnet, and that will create a magnetic field. Now you need to know the magnetic field that you are producing for a given current. So for that, before the start of the experiment, what we will do, we will basically calibrate this one. Okay. How will you calibrate it? So suppose you start the supply and then you have this separate gauge meter here. Okay. So what it can do, it has a probe, as you can see in the screen here. So you take out that probe and put it in between the pole pieces. Change the current that you are supplying. So this is your pole, the sensor of the gauge meter, and you have to put it in between the two magnetic poles. Then you change the current and you measure the magnetic field. Okay. Usually there is a linear response, but towards high current the response might not be so linear, but you will get a calibration current. So you will know for what current you can produce what magnetic field. Alright. Next we will show you the experiment.